Hi everyone, and welcome to the final part of the proof of Weyl's theorem. And now we'll take a grasshopper with step alpha, an irrational number, and this grasshopper is hopping or jumping on a circle. And we're concerned about the frequency of getting into an interval. As before, denote by m the number of jumps that occurred inside the interval, denote by n the total number of jumps. So among first n jumps, m of them were inside the interval. And this grasshopper, well, it starts from the beginning. Recall from the Kroneker's theorem that we know that jumps, marked points of the grasshopper will be such that at some moment after several loops, or maybe right immediately, some of the jumps will be arbitrarily close to the starting point, which means that we can make this interval, this distance, as small as we wish. Now denote this distance by beta, and it will be the same beta as in previous parts, and denote the number of this jump by g, but g is not for jump because jump starts with j. G is for grasshopper. And now, well, imagine that our grasshopper splits into g different grasshoppers with step beta. So this grasshopper with step alpha, one grasshopper with step alpha splits into g grasshoppers with step beta. Of course, beta is also irrational. We know that from previous parts. And g is the number of these grasshoppers. These grasshoppers start at the same points visited by the original grasshopper, but each of them has step beta. So imagine it's like you have not one grasshopper, but many grasshoppers with a very, very small step beta. The point is that marked points will be the same. These g grasshoppers and this one grasshopper mark the same points on the circle. Now, we need to learn something about the fraction m over n for the original grasshopper. Okay, let's transform these m and n into corresponding numbers for these new grasshoppers. These are like different personalities of schizophrenic grasshopper. Well, m is equal to m1 plus m2 plus and so on plus mg, which means that the number of times when the original grasshopper hopped into the interval is equal to the number of times when the first new grasshopper hopped into the interval plus the number of times when the second new grasshopper hopped into the interval, and so on. Similarly, n is equal to n1 plus n2 plus ng, which means that all of the first n steps of our original grasshopper are split among these g small grasshoppers. these G personalities of our original grasshopper. And we know that for each of these small grasshoppers, so for each g is a number of grasshopper, it holds that mg over ng is less than the same fraction, length of I plus beta over 1 minus beta plus gamma. Beta and gamma, well, beta is introduced here and gamma was introduced in the previous fragment, and greater than fraction length of I minus beta over 1 plus beta, let me put this into brackets, minus gamma. So this holds for each of these personalities of our original grasshopper. But from this it follows, that, well, m and n satisfy the same inequalities, because left-hand side here and right-hand side here are, well, they do not depend on g. So well, I need to write this because I cannot leave formula unwritten. I cannot leave only part of the expression on the board. And the main question is whether these boundaries, these estimates, help us establish such bounds. Length of I minus epsilon and length of I plus epsilon. Because what we wish to do is to prove that such fraction tends to length of I. This means, well, by definition of a limit, that for any positive epsilon, this fraction should be between length of I minus epsilon and length of I plus epsilon for sufficiently large n. So these inequalities should hold for sufficiently large n. And now just recall that these inequalities hold for sufficiently large number of loops that these grasshoppers make along the circle. But if n is sufficiently large, then the number of loops will also be sufficiently large. And recall that gamma can be chosen arbitrarily. For gamma, we choose the number of loops we need in order for these inequalities to hold. And beta, well, beta can be as small as we wish. Thus, it is rather clear that if we take an arbitrary epsilon, then this inequality will hold for sufficiently small gamma and beta. And also, we can choose such gamma and beta that this inequality also holds. So once again, we, for arbitrarily positive epsilon, we can choose gamma and beta, also positive. Well, of course, beta cannot be quite arbitrarily, but it can be arbitrarily small, and that's quite enough. Therefore, I believe that we have, by definition, a proof that this fraction tends to the length of the interval. Let me just write the statement of Weyl's theorem once again, and we'll finish by that. So, m over n, when n tends to infinity, is equal to the length of the interval. Well, this is Weyl's theorem. let me emphasize that we didn't use the existence of this limit. We actually proved that this limit exists. And this is the most complicated thing in the proof, because if we could use the existence of the limit, if only we could use the existence of the limit, it would be rather easy to prove Weyl's theorem. But unfortunately, there are no easier ways, at least I don't know of any, to prove the existence of such a limit. That's it.